Awesome. Welcome to the August Apache Cassandra contributor meeting. It's great to have you all here. Today, so in these meetings, we hear from people who are developing Cassandra and working on core features. And we today we're going to be hearing from Branimir Lambov, who's talking about Trie Memtable implementation in CEP-19. CEP is a Cassandra enhancement proposal, which is where all the core work gets done on Cassandra. So some great stuff going on there. Branimir's got some exciting stuff to share. I'll let him introduce himself a bit more, and then we can jump right in. If you have questions as we go, just drop them in the chat. I'll keep an eye on that as well, Branimir, if you can too. But I'll be keeping an eye on it and make sure we can get those questions answered. We can weave them in as we go, or have some Q&A time at the end as well, and then we'll wrap up when we're done. So yeah, I will hand over to Branimir. Thanks for joining us, and I'll let you introduce yourself a bit more and your topic. Over to you.
My name is Branimir. I work for DataStax, have been for 9 years now on the core database on Cassandra. Usually the stuff I do is on the local node processing, the storage, and bits around that. And this example, this CEP that I'm going to talk about today is, again, one of those pieces in the local node infrastructure in Cassandra. As I already mentioned, I live in Bulgaria. I started working in London and moved back here. That was one of the big advantages of working for a company like DataStax. You can just work from anywhere in the world. So starting with the starting on the topic. What are the memtables? So generally, Cassandra is an LSM, log structured merge tree database, which means that it's built of data stored in multiple components. When we read it, we need to consult multiple components, and then we write to the database. We first write to a buffer, which is this memtable, which takes a few writes until it fills up, and that memtable is converted into a non-disk SS table. Its purpose is to sort and organize the data so that it's efficient when it's written to disk, and it's also a source for any reads of recently written data. One of the effects of the fact that it's accepting all the writes is that we can't actually acknowledge a write until it has completed its work in the memtable, until it's ready to be served to other readers of the same piece of data. So it's on the synchronous path of every write. Every write has to wait for the memtable work to complete before it can acknowledge things. Now, the interesting thing about memtables is that they're actually considered fast enough, because there are so many other overheads in the system that usually the work we do for the memtable is just a very small part of it, especially if you're doing reads and you're consulting a disk. The memtable is going to be nothing compared to reading from disk. And yet there are a lot of things that can be achieved by optimizing memtables. Maybe the focus of doing this has to change a little bit to do this, because to make things better, generally, you don't just want to improve the performance or the speed with which you can write or read through the memtable, but you're more interested in how much space a memtable takes for the same amount of data, and whether or not it has a complex structure that a garbage collector needs to look at, and how much time it needs to spend processing and dealing with this memtable structure. Now, to continue the discussion about why we want to optimize the memtables, let's look at what the existing or the legacy memtables in Cassandra actually are. They're a hierarchy of maps, and they're comparison-based maps, which means that the only thing we we know about the keys are that we can compare to different keys, and based on the result of a comparison, we can choose whether to go in a structure. So there exist many structures that can work only with comparisons, such as B-trees, concurrent skip lists, any type of binary tree or just ordered tree, and many others. But you can't use hash maps, for example, because we need the memtable, as any other structure in Cassandra, to be ordered in a way. So what we use for in the legacy memtables is a hierarchy of such maps. On top, there's a concurrent skip list, which is a map that gives you every partition for a given partition key. Below it, there's another level of maps. So for every partition, we have a separate map which indexes rows within the partition using a B tree. And for every row, there can be another level of maps. There can actually be even two levels of maps indexing individual columns, and individual cells in the row. The data, the actual values of cells in the memtable currently can be stored off heap. So we have some management mechanism that allows us to put the data for cells in off heap memory. But all of the maps, all of these structures for all levels of the hierarchy are on heap. And they're actually a pretty complex structure because you have an index for the partitions, then many indexes for each partition to individual B3, to individual rows. And for every row, you also have another level of a B tree, which gives you all the columns in the row. And this quickly becomes huge. And because this data is on heap, this has two very big disadvantages. The on-heap size of this SS table is, of this memtable is bigger than the data size most of the time. And by not a small number, it's several times bigger than the size of the data which we put off heap. Also, this structure is very complex. So when the garbage collector decides to walk this structure, it has to spend a lot of time following pointers. It also is not short-lived, which would be ideal for a garbage collector. Neither very long-lived, which would also be good because it can be left alone in some older generation. It has a medium-term life cycle, which means that it has to be promoted. But after it's promoted, very soon afterwards, it has to be removed again. So that's the worst case scenario for garbage collector. And this structure changes all the time when we're inserting data. So these objects, which are not short-lived, they change a lot. New ones come in, older ones disappear. And this is just a lot of work, which is not simple for garbage collector. It's also that this structure is generally, we want it to be as big as possible because the size of this structure determines the size of the lowest levels of the SS tables, L0 in the compaction hierarchy. And that size of L0 determines how many levels of compaction you need for the same amount of total data. So if your memtables can be bigger, your compaction hierarchy can be shorter, which means that your reads can be more efficient at the same number of overwrites, or with the same amount of work you have to do for every write. So we want them to be big, but big mean more compaction, more garbage collection, less compaction, but more garbage collection. More garbage collection, especially garbage collection that needs to deal with with older generations, means longer garbage collection pauses. And these are one of the things that we really want to get rid of in Cassandra. So how can we improve this? Let's start with the idea of these comparison-based structures that memtables use. Now, we have keys which are composed of multiple components. So you may have two columns forming a partition key, another three columns forming a clustering key. And every time we want to find where something is in a map like this, or we want to insert a new piece of data in a map like this, we have to compare the existing keys, some of the existing keys to the new key with all of these components. Because we often have repetition of deleting components with just different value of the end component, often when you're doing these comparisons, we have to compare again and again the same prefixes, which is one of the reasons why we actually have to introduce compaction. But we have to introduce map hierarchies in memtables or other things like this, so that you can avoid having to recompare again and again, for example, all the components of the partition key when you actually want to go to individual clusterings or individual rows within a partition. You would prefer not to look at the partition key at all, just, if possible, at the last component of the clustering key, to be able to find the row you're looking for more easily. We don't do this at the moment, so we only have a hierarchy split at the level of partitions. So each of the components of the clustering key are going to be compared all the time when you're doing comparisons and comparison-based data structure. One of the other things that's bad about this is that all the keys always have to be prepared in a form that's ready to being compared, which means that it's pretty hard to store them in some flat storage op heap or something like that. The keys have varying lengths, which makes, again, memory management and garbage collection a little bit harder. These repeated prefixes can be causing problems. And we also have a complexity, which is the length of the keys multiplied by logarithm of the number of keys we have in the map, which is good, but there are structures which can do a little bit better. And these structures rely on the so-called byte order. If you imagine strings, for them, you can compare two strings, and the first time you see a difference in a character at the first different position in the string, you know which of the two strings is smaller than the other one, because they're lexicographically ordered, which means that which means exactly this. The first time there's a difference, order is determined. We don't have this in the normal types for Cassandra. We have to fully look at the full value before you can compare. For example, if you have a big decimal, big integer, or just a floating point number or an integer number, you have to take all of the bits of the number, and you directly compare all the bits with all the other bits of the other number. So the thing about byte orders is that if you have them, you can decide comparisons early, but also you can use structures that make usage of this internal, this structure of the values. And these structures are called tries, and they have a few advantages. One of them is that when you store a lot of information in a trie and you have repeated prefixes, any prefix is stored only once. In this example here, to the left side, you can see a lot of words that all start with A, and the letter A is represented only once in the edge that goes from the root to the node marked with A. We don't have a repetition of this letter anymore. For all of these values, it's repeated only once. This automatically takes care of these hierarchies that we have to do for the memtable in the comparison-based case, because when we have a hierarchy like this, and when we have a prefix that is the same for multiple values, this prefix is going to be stored in the trie only once. Another thing about this is that we know that every node has only up to 256 children, because these are all the bytes, all the possible values of a byte. So we can, we can use some data structure that uses only up to this number of children. Also, to look for something in a trie, you follow the transitions. And if you're looking for example, the first thing in the trie, which is greater than, let's say, together, that would be following the first character of the word you're looking for, which is T, then following the second character of the word we're looking for, which is O. This brings us here. We have more characters, which means that this is not the value we're looking for. We're looking for something bigger, and this means that we can just go back one step and follow, and by following the first transitions afterwards, this is going to lead us to the node which is greater than, which is the closest greater than the word we're looking for. Yeah, I talk about words because this is the terminology that was originally used for, tries were originally used for words and storing dictionaries. A word in our use case is just a sequence of bytes, which determines some key. Yeah, so lookup in a trie, because we're following always one transition in the key of the key, one byte of the key is just an O of k operations, because the length of the key is k. We're just taking one transition for every character of the key, or any character of the first value after we found the point where we can just find the next value. In general, here, if we have byte order, like for strings, we have better understanding of the keys in our database, which can lead to better efficiency, looking up data, inserting data, and also taking space to store the same amount of data. The problem for Cassandra is that most of the types in the database are not things that are naturally byte ordered. We have to convert them. This is something that we can actually do. It's not too hard. And for most of the types, it's actually very simple. For example, if you take integers, if you just take their byte values, you have a little bit of a problem because positive integers start from 0 and end at 7f, and negative integers start at 80 and zeros, which means that if you directly compare them as unsigned bytes, the negative integers will come out as greater than the positive ones. But you can fix this by just flipping the top bit of the encoding, and then all the integers start at 80,000, and all the negative numbers end at 7ffff, and they're smaller than the positive ones. You can do a very similar trick for floating point numbers, and actually you can do something like that for all of the types that Cassandra can use as keys. One other thing that's important is that you can also take multiple keys and form one single sequence of bytes, which is an encoding of all of the sequence of keys. And it's also something that can be compared directly as a byte sequence, and can give you something which is equivalent to the multi-component key. For example, for the multiple components of the partition key, and also the token, which is usually sits at the front of the sequence of keys in the partition key, you can combine all of these components into a single byte comparable sequence, and you can use that and put it in a trie. And that's the main idea of the new Memtable solution. We have a translation of this key, of this multi-component key, into one single byte ordered sequence. We put this in a custom trie, made to be as efficient as possible for Cassandra. This trie is a single writer, multiple reader thing. So if you want to have good performance in multi-threaded machines, in multi-core machines, you actually need to shard the memtable, but it's separated into several components, split by token ranges, so that you can do multiple writes in parallel. And then the implementation of the Memtable itself is using some interesting features to make it as efficient as possible. The first thing I can talk about is the type of Trie Notes. So when you build a tree of data, something that very often you can see is that you have a tree which has a lot of dense nodes, that is, nodes that have many, many children, very close to the root. After that comes a space with lots of nodes with very few children, up to 2, 3, 5, 10, usually not more than that. And below this, in the tree, you see a lot of change of single child nodes. And at the end, you have leaves. And if you count the nodes that are there, most of the nodes are leaves. Then you have a lot of chain nodes. Then you have quite a few sparse nodes, and the dense nodes are fewest. So it makes sense to try and optimize the way the data is stored, to take advantage of the fact that we have 3 different kinds of structure in the trie. And you can do things like save time by using pointer arithmetic for the ones that you are close to the root and are consulted most often, because you always have to go through these to find any piece of data. When most of the children are either leaves or single chain ones, you can combine single child chains into sequences to save some space, and also to save some time by looking at things that are positioned very close in locality to the previous node. And also you can save space by not saving space for all the children of a sparse node, but just listing a few transitions with their targets. And at the end of all of this type nodes idea, you don't even need any space for leaf nodes that have only a pointer to some piece of data on the disk, because you can use the pointer to give you an index in an array and completely say storing this in the trie structure. One of the other important bits about the Memtable trie is that we use a fixed block size, which makes it much easier to do memory management in the trie structure. So the idea here is that we want to do our own memory management. We want to use an off-heap block of memory or an on-heap block of memory, but the thing is, we don't want to give the garbage collector access to the individual pointers, individual blocks. In this, we want to manage them ourselves so that the garbage collector sees just the one big blob, never looks into it, and so garbage collection cycles are faster, and there are no garbage collection pauses or shorter garbage collection pauses. The way we do this is by managing ourselves what blocks we take, what blocks are no longer needed and can be reused. And to do this most efficiently, we use the fixed block size. This is 32 bits in the 32 bytes in the current implementation. And because 32 bytes are not enough to fit all of the 256 transitions that at most you can have for a single node, we do a different trick. We instead do sub-transitions. So we kind of change the width of a transition that we need to take when we're in a dense node. We first take the first 2 bits, which takes us to another subnode. We take then the second 3 bits in the value of the character we're processing, which takes us into another subnode, and then the final 3 bits of the character we want to process, the byte we want to process, gives us a pointer to another to the next node in the trie. So in fact, we have 3 nodes on this path for every dense node. So the dense node is from the point of view of a user of a database of the Memtable, and the sub transitions or sub nodes are from the point of view of storage in the Memtable itself. So By using these, we can fit the dense node into multiple of these fixed block size blocks. And yeah, you can, what was the number? We can have up to 8 times 8 plus 1, so we can have up to 65, I think, nodes that form one dense node if it's fully dense, if it has mapping for every child, for every possible transition. But it also allows us to get rid of some of these children and make it take less space. If, for example, you have characters in an alphabet where, for example, if you're using ASCII characters, the second half of the byte values are never used. So we can, by using these sub-transitions, we have half of that space that's necessary for these children. It's not used ever, so we're not taking any space for it. The other side of this, of taking advantage of this fixed block size, is when you're closer to the leaves, when we're in the spaces of the Memtable Trie, which have only a single child, we can combine multiple such transitions into one single block. So in the example here, the chain that starts at OX18 has several transitions, and all of them are in the same block, actually 00 block, which extends from the address 00 to the address 01F inclusive. And in this one, in this example here, we have 4 characters being 4 transitions and 4 nodes being placed into the same block. And the pointer after it takes us to a entry in the content array. So the value that's associated with the word TRACTOR or tractor. Using fixed block sizes has 2 objectives. One of them, as we mentioned, is the possibility to do memory management efficiently. And the other is that every time we're actually reading data from memory, we're fetching a cache line. And cache lines are usually at least 32 bytes. Some, as far as I know, they're getting bigger all the time. So they're probably, the next iteration of this will have to use 64 bytes or something even bigger. But the thing is that when we're accessing even 1 byte, we're taking the whole cache line with us. And it makes a lot of sense to be to take the most advantage you can out of this whole cache line that you've brought in. The other thing I mentioned is that we use pointer tagging, which means that we store integer pointers in our data structure, which have some bits that determine on one side what kind of node is this node we're looking at. So, for example, sparse nodes end at E and 1. So the last 5 bits of a pointer are actually these tag bits. That's because we have 32 bytes per block. So all of the last 5 bits give us the block ID, and the last 5 bits are information about what is the type of node, and if the node is a chain node, we actually know which one node we're actually looking at inside the chain. So, for example, these OX19 here points to the node with pointer T, and the target of this transition with the character T is just the next address, which is OX1A. It doesn't need to be written anywhere because it's because that's the way that the chains are stored. The other usage of these tag nodes is for leaves in the trie. We store a negative number, and this negative number maps into an entry in the content array. So in the array of the values that we have for that trie position. Using a negative number means that we don't have to actually reserve a block for the leaf. just use the pointer directly, the pointer value directly. Now, one thing that's important about, another thing that's important about these tries is that we have a very efficient way of walking them, which basically using a so-called cursor, we can, when we're trying to list all the keys and values present in the try, we can do this with a very efficient mechanism where we use a cursor, which is something that walks the try in lexicographic order. So it walks all the nodes in the try, not just ones that have content, but just everything. So in this example, the first node we want to visit is T, because out of all of the nodes here, this is first in lexicographic order. Then the next one is something that extends this word we've collected so far with another character, and that's R. The third one extends it with yet another character, A, and so on until we reach the tractor point. And then the next one in the lexicographic order is moving back up the chain and using the next transition of the first closest node that has any next transition. And this brings us to the tray node. Doing this means that we need to visit we visit all the nodes in the try only once, exactly once, which is as efficient as it gets. And you also have sufficient information to be able to build the paths for a user to be able to build the paths out of these steps that are given to you. And it's also very easy to combine, to walk multiple tries in parallel, and to tell which position in which try is earlier than the other one, which is very important to be able to build a union or a merging of multiple tries, which we use where we're collecting information from multiple sources or when we're doing things like compaction. So unions and intersections are done on cursors, and the great thing about this is that there's no, you never need to create a new object to track the state of in the try. There's no new iterator being created every time you have, for example, to list all the rows in a partition, which is a problem that we have right now with compaction. Compaction is not efficient for skinny rows, skinny partitions with just one row, because every time we are processing a new partition, we create another iterator for the rows. So in a cursor paradigm, where we actually walking them using these depth and incoming byte, this cursor paradigm, you don't need to create any new object for any new level of the hierarchy. Yeah, this makes it as efficient as can get for walking something like this. Well, the most efficient way of walking data is to have a linked list at the bottom and to just follow this linked list. But the problem with having the linked list at the bottom is that in that case you need to store the keys of each partition or of each element in this linked list, and this defeats the purpose of the try, which is to only store the paths, the keys in the paths of the try, and that way to be able to come to very efficiently to use prefix sharing and to remove a lot of the repetition of the keys and to just store the keys as efficiently as possible. So this gives us a sort of a middle ground where we have a very fast reversal, but we don't need to store the keys in a linked list at the bottom of the structure. Now, what do we get out of all this? I already said that being faster is not really an objective. It doesn't matter that much, but still we do get faster than the legacy Memtable implementation. In this case, it's about 2 times faster, 1.8 for random reads, more than 2 times faster when you're trying to insert data. The more important bit is, though, that we can fit much more data for the same on-heap size, around 30%. This translates into bigger SS tables on the lower level of the hierarchy, which in turn means better compaction afterwards. When we use the new Memtable for a longer period or in a bigger test, we can see that this throughput advantage, this advantage in the time it takes to write translates into a much better burst throughput than using the legacy Memtables. And if you optimize things a little further and use better compaction, you can also maintain this higher sustained throughput. When you're doing a much longer process, in this case, it's more than 20 hours. For the blue graph, it's more than 10 hours. The efficiency or the processing time of the Memtable stops to matter that much. And the thing that becomes more important is the size of the SS tables on level 0, which we already said that we improved, and also how much work garbage collection has to do. And we improve all of these things so we manage to get much better longer term performance as well. Latency reduction at fixed rates, and what we wanted to achieve, much better total garbage collection time than the legacy Memtable implementation. One of the things that may worry some people is the fact that we do sharding, which means that we split the Memtables into several independent components so that you can write in parallel to each of these components. Because the keys are hashed because every partition starts with a token which is hashed, this usually gives us pretty good distribution of work, and you can achieve a better performance that you can achieve even with a data structure that's meant to be concurrently modified. In this example here, the first graph is without any, with randomly distributed load. And in this case, you can see that the parallel structure, the skip list, is actually slower than a different version of the same structure, which is sharded, and that is much slower than the Trie implementation, which is again sharded but faster in individual operations. And actually, even if the sharded skip list is blocking, which means that it's only accepting one write at a time, it becomes faster than the other alternatives, even though it's blocked, because we can take more work and we can switch between the threads processing individual shards. It's actually more efficient to do blocking than to do parallel processing here. The thing changes when you do more access to the same key. In this case, you have to, you're actually hitting the same shard many more times. And if you're half of the time you're hitting the exactly same value, you can see that the skip list, the parallel structure becomes faster than the blocking structure, and the trie becomes even slower. But 50% skew, half of the access is hitting the same key, is not something you actually expect for users of the database. I would say something like up to 10% or even 20 would be normal, but 50, not something that you would be expected to see in real scenarios. Yeah. Now, how do you use this? This may change by the time Cassandra 5 is released. Now, the new implementation of the Memtable is part of Cassandra 5. The way it can be turned in the current versions of the code is by adding a little bit of information to Cassandra YAML to define a new Memtable type. You do this by setting Memtable Configuration, specifying a specific configuration, giving it your name, in this case, Trie, which refers to the class name Trie Memtable. The next two lines change the default for the node. So every time you're creating any table, if you've added these two lines to the Cassandra YAML, it will always use the Trie Memtable. You can also use it per individual table. And to do this, you have to specify the Memtable as a parameter to create table or alter table. This here, Trie, refers to the definition of Trie given under configurations. So yeah, so if you want to use it individually per table, specify it for only some tables and use the default for others, you would use the same the first 4 lines of this configuration in Cassandra YAML without the default part, and you would specify it in an alter table statement for the table you want to use it on. Now, one of the important things about this work is that it's not finished at all, and it enables a lot of things. One of the things, the first thing that it enables is in Memtables to completely eliminate the map hierarchy. So instead of this skip list map that takes us to a partition, and each partition has another B-tree map which takes us to the row, and each row has another B-tree map which takes us to columns and cells. Instead of this, we can have one big trie which has some just some pointers that at some point tell you, well, this is the partition boundary, and then it continues onwards. And then at some point it can specify and can say that this is a row boundary, and it can continue onwards to individual cells. So everything can be stored in one single trie, in one single object in memory, which can be completely something that the garbage collector doesn't visit, which means that we can have very, very fast garbage collection cycles and no garbage collection pauses at all, because most of the other stuff which is in Cassandra is either very short-lived and can be very quickly processed and thrown away, or permanent, in which case it can live in some older generation, not be touched by the garbage collector almost never. That's one part of it. Once we do this, it also lets us eliminate the iterator hierarchy. The iterator hierarchy is the representation counterpart of this map hierarchy. So when we're trying to read from disk or from the Memtable, and we're trying to generate output for the user, we're using an iterator that walks all the partitions we've selected, and for every value that this iterator lists, we have another iterator which lists every piece inside the every row inside the partition. Now, because this second iterator needs to be created every time, this is overhead that's causing some problems, and the code is much more complex than if we had a flat hierarchy, which would be enabled by a cursor and this view of the whole data store as a trie. It then enables a more efficient on-disk format, because when we've defined these things, it's very natural to store them in a format which is the direct serialization of what the iterator sees. And once we do this, it's possible to, we have an opportunity to also change how we store some values and how we store metadata in a way that lets us do much more efficient compaction. Mostly being able to see at some point that all of this that's below this point in the trie comes from only one source, only one SS table. Let's not look inside it at all. Just take it as it is as bytes on disk and move these bytes to another file. Having this can improve performance of compaction tremendously. It can take it close to the write speed of SSDs, and would be great. Another thing that this makes possible or gives us an opportunity to do is to tolerate tombstones, meaning that if we define a good way of representing tombstones in this map hierarchy, we can do it in such a way that we can have millions of tombstones and still be able to read data without visiting, without seeing these tombstones, without caring about them, generally. We know that tombstones are a problem for Cassandra, and this is an opportunity to completely solve it rather than trying to reduce the number of tombstones, just not care how many there are. And towards the end, if we have a representation of data in this big trie with these simple flat keys, byte sequences, we can also change the way partitioning is done, meaning that we can start using some prefix of this long byte sequence as the boundary between nodes. So right now we have we can only use tokens as the boundary between nodes, which gives us problems if we want to have, for example, tables which are completely ordered, which you may want in case of trying to do, for example, a global secondary index or a materialized view or something like that. And if we're able to decide to split data anywhere in that key for any prefix of that key, we can use a prefix that extends into the clustering keys, so we can actually split or shard data that resides on one single partition to multiple nodes, which would be part of a solution to the problem of to multiple problems, to hot partitions, to very wide partitions, and to also the use case of completely ordered tables. This is all from me. I don't know how understandable this was.
That was great. Thanks, thanks, Brandon. I appreciate it. Thanks, folks, for listening. That was really cool. Do you just, if there's any questions, feel free to drop them in the chat. And also, the recording of this meeting will be up on YouTube either later today or tomorrow once we've got it processed on the Planet Cassandra YouTube channel, which you can actually check out for other contributor meetings and also town halls recordings all up there. I can drop the link in the chat. Actually, you can have a look at some recordings on there. Always great to catch up on those. Yeah, so thank you, Brandon. That was great. Appreciate you taking the time to share with us. And yeah, excited about this work going into Cassandra. Before we close off, just a couple of announcements. One is a reminder. So on December 12th and 13th, we've got Cassandra Summit coming up in San Jose, which is very exciting. You can get your tickets now. You can register for it right now. I just dropped a link to it in the chat, so you can get your tickets for that. And also, we have our next contributor meeting will be on the 26th of September, 10 a.m. Pacific. We'll announce once we've got confirmed, we'll announce a speaker and the topic for that, and it'll be on the wiki page, which I just dropped the link to as well, so you can check that out. Be the same Zoom link, and yeah, that's going to be great. And then we've got a end of September, 28th of September, 8 a.m. Pacific as our next town hall, which we will announce the speaker for that soon. We have that confirmed. We're just nailing down a topic, confirming a topic for that, and we'll have that published ASAP. And you can join the Cassandra meetup group to get updates about that. As soon as it's announced, we'll send an email out to the whole group and post it in Slack and everywhere else, so you'll get info about that. But that's it. Thank you so much. Again, the recording will be up online later, so you can check it out and share, and it will be linked on the wiki page and conference as well. So thank you for joining, everyone, and thank you for sharing, Branimir. It's been great to hear from you. Thank you. Cheers, everyone.